So let me start this afternoon session. Our first speaker for this session is Rolf Hoffmann from the Technical University of Darmstadt. Please, the floor is yours.
Thank you very much for and I also want to first express many thanks to Franco for organizing this very nice workshop and for the kind invitation. And I want to talk about tiles and how tiles can produce simple 1D pattern. This is an outline of my talk. What is a one-dimensional pattern? What is a 1D CA? And then about simulation and different updating schemata. And then the problem which will be studied, how patterns can be generated by a certain cellular automata rule. Then about tiles and so-called templates. And then about the cellular automata rule, how it works. And then something about using more cell states and several tiles and so-called empty pixels, and conclusion. So what is a one-dimensional pattern? It's in the binary case, it's very simple. It's just a binary string. It's nothing special, very easy to understand. And of course, we can use a stripe-like 2D representation to just stretch the bit string in the second dimension. So stripe patterns can be seen as a one-dimensional string pattern, let's say. And we can observe in everyday's life and in nature and decoration, clothing, and almost every day and everywhere we can recognize such patterns. And I brought from Danst, Barbara, if you can please show your clothes. This is a very nice stripe pattern, which you can see. Thank you very much for presenting your stripe patterns. It's a very nice stripe pattern, which you can see. And what is the problem? The problem is how can they generate it? And with a certain structure. There are certain stripe styles, as you can see here. And even you can consider them as art. I was once in a museum in Basel, and I saw such 1D patterns which can be interpreted as art. And even if you go to the center city, you will notice that there are some stripe patterns. Yeah, but it needs that you just recognize them. If you just look at the building, probably you don't see them very clearly. You see the building, but you don't see actually usually these stripes because they are very common. And I will talk about a CA rule, which was already applied and in TD, two-dimensional, to generate point patterns. or to generate so-called domino patterns for instance, in the diamond, where you place these dominoes in a certain environment. I think, meanwhile, all of you know what is a one-dimensional CA, cellular automata. It is an array of automata, and each of these automata apply a certain rule to a state, compute a new state, and then usually in a synchronous manner, the new states are written back to the state, overwrite the state. But what is important and usually is not very clearly expressed, that you need two memories. It's not sufficient to use one memory. You have to use the current state and the new state. And then you need an update phase. So we can use synchronous and asynchronous updating. Here is the principle of, let's say, programming cellular automata. It is very easy. And we have, in the synchronous case, we have the cell state is a triple of the current state, the new state. And in our case, we use a hit variable, a local hit variable, which I will explain later. And what you have an array of cell states, array of next new cell states, and the hits I will explain later. And this is a simulation, which is very easy to program. The loop, outer loop, for the number of iterations, the time steps. Then you iterate for all cells. You first compute the number of hits, which I will explain later. Then you compute the new state by the rule, taking into account the neighbors and the hit value. And then you need, in the synchronous case, you need an update phase. If you use hardware, let's say flip-flops, in every flip-flop there are two such memories. And if you use the clock, then you have two phases, but it is because they are triggered by the clock. And now we come to asynchronous updating. In the asynchronous case, the cell state is simpler. You have the current state, and in our case, additional hit variable. And now we iterate, we make Tmax iterations, and within each iteration we have n so-called micro steps. I call them micro steps per time step. First, we choose the position of the cell X at random. We compute the hit number. I explain later more details. Then we compute the new state by the rule, the neighbors, and the hit value. And then immediately we update the cell. So at each micro step, the new cell state is computed and updated. And we define that n micro time steps are performed during one time step. And the configurations are considered at time steps. They are sampled, logged at time steps. We can use the different asynchronous updating variants. One which I call is pure random. You just select at random the cell and then you update the selected cell. Random sequence means that you, for each new generation, you use another sequence of, let's say, a random permutation of the cell indices. And you may also use a deterministic way of updating. And now what is the problem? The problem is to generate stable 1D patterns using potentially overlapping tiles. Here you see the problem. We have a 1D space, cell space, with the cell states here. And we restrict at the moment for 0, 1, and 2 state variables, cyclic boundary conditions. And we use a set of tiles, G1, G2, and so on. And each tile is, let's say, array of, in the binary case, it's just a binary string, a small binary. For instance, white, black, white, 0, 1, 0. Or we can, of course, we may use more another state variable like 2, if, or even more if you want. And now, what is the question? What kind of patterns can be generated using a simple cellular automata rule, which I will explain later. And we will also see differences in synchronous and asynchronous updating schemata. We have here a simple example. The tile which we use is 0, 1, 0. And how can we arrange them? We can arrange them just one after the other with no overlap. And we call such a pattern a minimal pattern, or for short min pattern. We use a minimal number of tiles. They are not overlapping. And in this case, here we have the high overlap with a maximal number of tiles called max pattern. We have here, we see overlapping. We are allowed to overlap the tiles if there's no conflict. 0, 0, we can overlap the tile. Okay? Here's the overlap, overlap, overlap. And in this pattern, we have a partial overlap. We have overlap here, 0 and 0 overlap. But, oh, sorry. And here in no overlap. Okay? And the question is now, what what kind of patterns are generated? All the patterns which may overlap, but need not to be overlapping. And now the tiles and templates, more and more details. As the templates, the tiles are used to cover the space, and the templates are derived from the tiles In principle, they are local matching patterns. A tile is a string of tile points, GI, in a certain radius, a small pattern. A small pattern which 0, 1, 0, for instance. In addition, we can use a so-called empty point, a not covering point. We may use a tile which has a space in between, or many spaces. So let's say, for instance, a pair of particles which are connected, but they have a gap in between. We may even think of a tile as, let's say, as a complex particle. You have to have in mind that it can be a sort of particle. Pardon. Okay. So templates are local matching patterns, and the condition for a valid pattern is that we have everywhere we have a so-called template match, and the whole space is covered by tiles, and the tiles may overlap. And these templates, these matching patterns, are derived from a tile by all possible shiftings. We see example, next slide. This is a simple tile, 0, 1, 0. And what we do, we are shifting the tile to the right, to the left. Any possible shifts which are useful, and we shift the tile to any position, and we receive the set of templates. And these templates, these are used as matching patterns. The center pixel is called reference pixel, or with a certain reference value. This is reference value 1, reference 0, and so on. In the middle of the template, of the shifted tile, this is the reference, the center. And now we come to the rules. First, we compute the number of hits, the number of template hits. At the selected position, we check for all these shifted tiles, for these templates, and we register a hit or no hit. And we store this number of hits. Then we apply the rule, taking into account the hit number of hits, and then we update. Then we have a simple rule. If we have no hit, no template match, we inject noise. Very simple. If we have no matching pattern, we inject noise in order to drive the evolution to a valid pattern. And if we find one or more hits, we adjust the central, the state of the cell to the central value of the template. This is, let's say, the correct value. We see an example here. First example for tilings, and then I explain again the rule in example. For instance, if we use 3 cells, we use just one tile, in the simple case 0, 1, 0. For 4 cells, we get this pattern, only one solution, with one overlap here and one overlap here. For N5, we get this solution here, one overlap here. N6, we have 2 solutions. One so-called min pattern, I explained already, no overlap, and so-called max pattern, two overlaps, 3 overlaps. 2. This V means is the cover level, the number of overlaps. So here we have a simulation of the rule first by hand. This is we have 3 templates, which I explained already. This is a shifted tile. And we select this cell. We check for templates. We find one matching template. 0, 1, 0. 0, 1, 0. We don't consider the actual value of the own cell. We find 0, 1, 0, 1, but the correct value should be 0. We correct the wrong value 1 to 0. So what we do, if we find a template match and we don't care about the central value, then we do a correction. And otherwise, if we have no hit, we inject noise in order to drive the evolution. And here you see simulation by simulator. You can see that very quickly we find a stable pattern. And this is a min pattern with a minimal number of tiles, 2 tiles in this case. And here you find a more detailed simulation, and where you register the number of matches, the number of overlaps, the cover level, the number of hits, and so on. This is most of the work when you write a simulator, or to make these details, input, output, and so on, so on. And here's another simulation. And you find another solution, so-called max pattern with three tiles. And in this case, you have a high overlap. You can see it here. I have explained before. So if you, let's say, run the simulator, you find different solutions with high overlap and others with low overlap. And for instance, if for 24 cells and 1,000 runs, you find a certain distribution of the patterns, and min patterns, you use 8 tiles, for example, and max pattern 12 tiles. And you find a certain distribution when you run the simulation, and you get such results of stable patterns. But you are not sure if you get a minimum with a minimum number of tiles, maximum, or in between. And if you take the average, it is here in the middle somewhere. And what is interesting, let's say, maybe from the physical point of view, that you can consider the tile as a particle, let's say, and these particles keep at a certain distance. Keep a certain distance, okay? Min patterns, if we want to drive the evolution to certain min patterns with a minimal number of tiles, then you can inject additional noise where in the case where the cover level is higher than 1. Is written here. The idea is to inject additional noise where you have a high cover level, where the hit number is greater than 1. And what is interesting, the hit number is an approximation of the cover level. The cover level you can compute globally, but the hit level is computed locally, but it is only an approximation. But interesting is that we can use this approximation to drive the evolution in the right direction. Here we can see a simulation. Just shows that it works, let's say, and we find a min pattern. And now we can, what can we do more? We can use more cell states. For instance, 0, 1, and 2. And for instance, the tile is the 2, 1, 0, and here are the templates, and we get such a pattern. What about synchronous updating? Now, before we used asynchronous updating, I did not tell it. In asynchronous case, we have very fast evolution. And in the synchronous case, it is, let's say, more complicated. If we use a rule from asynchronous updating directly, what we observe some oscillations. Because if I update my cell to the correct value and my neighbor is doing the same, it may be not good for my neighbor. If we do, both of us update to the correct value, but it maybe is the wrong decision because my correct value may be not correct for my neighbor. So we end up in oscillations, or let's say some live logs or something like that, some oscillating or repeating patterns, and we do not reach a stable pattern what we want to do. And what we can do, we can inject extra noise. We have to block these synchronous oscillations by injecting some noise. This is the only trick that has to be used. And then we end up also with stable patterns here. And now several tiles, empty pixels. For instance, we can use 2 tiles. For instance, we want to model some arrows or some charging of particles plus minus, and then we can use such 2 tiles. One is for plus, one for minus, and we can investigate all the combinations, and we can see that there are certain combinations of plus minus. This may be interesting for some particle systems and some certain conditions on us. But we have carefully to select tiles. And here are some simulations, and we end up with such resulting patterns. And I come to the end, and here we have what is interesting. We can use such empty pixels for instance, 0, empty, 1, 1, empty, 2. So we have, let's say, two particles which are connected, but with a certain distance. And then there is an example for an evolution which you can hear in the synchronous case. So I come to conclusion. We have used a probabilistic 1D rule to generate stable patterns, and the templates are derived by shifting. And in the asynchronous case, we very quickly arrive to stable patterns. In the synchronous case, it's more complicated. We have to inject additional noise. And we can also use distant pixels, which may be interesting for future work. We can use more states, of course. In principle, we can find classes of patterns with certain properties, symmetries and distributions and so on. We can try to drive the evolution to a minimal or maximum number of particles, let's say. And we can, yeah, avoid oscillations. Relates a problem to the graph vertex cover problem on, or it can try to use to model particle systems. Thank you very much for your attention. Thank you.
Thank you very much for this very interesting talk. I've got a question for you, but maybe someone else wanted to ask something. If not, then my question is about the possibility of generating more complicated patterns. I thought, for example, about quasi-periodic sequences. Do you think that it will be possible with that method, like, I don't know, binary Fibonacci sequence, you know, where there is a given algorithm for the sequence, however, it is not random and it is not periodic at the same time, right? It's quasi-periodic. Do you think that it is possible? Such rules?
I think this approach has a lot of possibilities. I'm not sure if it is possible what you have in mind, but I think there are quite a lot of possible ways to make such patterns.
Yes, because, well, for example, this binary Fibonacci sequence is about replacing 0 with 0, 1, if I remember correctly, or something like that. So there are some rules in terms of algorithms. So I guess my guess is that it would be possible with that kind of cellular.
Maybe some extension, I have to add it to this idea, yes.
Okay, thank you.
Mm-hmm.
Are there any questions? Yeah. If not, let's thank the speaker again. Thank you.
Thank you very much.
And the next speaker is Milan Ismail from Kent University, right? I tried to pronounce that correctly, something that I know from your speak. I always thought that it is Ghent simply, which is not, right?
In English it is.
It is.
In Dutch we say
Ghent. Okay.
All right.
So in the meantime, let me tell you that Milan will tell us about the structure of the cellular automata rule space,
yes,
right?
That's something that I'm working on, that I hope to publish, but yeah, it's still in the earlier phase, but I can already show some of like the basic ideas. So SummerSolstice. Yeah. What I'm doing is a little bit related to what Michiel already talked about, but yeah, I'm taking quite a different approach. All right, so yeah, the topic of my presentation is the structure of the stellar automaton rule space. So first I will kind of, oh. How do I do the laser pointer? Ah, okay. So first I will kind of generally frame the issue of yeah, that there is a lack of structure or basic structure in the rule space and how it can be fixed by introducing a parameter or parameterizing the rule space. Then I will discuss some of these parameters. Then I will talk about mean field theory because I will propose 2 new parameters myself, and these are both based on mean field theory. And then finally, I'll show some phase diagrams or some structures you can get from these techniques. So yeah, basically the rule space is just a set of all possible updates rules for fixed k and n, where k is the number of states a cell can be in, and n is the size of your neighborhood. So for example, for your elementary rule space, you have the number of states is 2 and the neighborhood size is 3, so you have 256 possible update rules. But there is no inherent structure in the rule space, so there is no real way to say if rules are close or not. Of course, you can always say they are close if their rule table differs in just one bit, but still that doesn't give you a convenient way to visualize the rule space or give it like a phase diagram. And also, it's not because the rule table is similar that the behavior is necessarily similar. So one thing you can do, of course, is to impose a structure on the rule space is to parameterize it, meaning you look at the rule table and you associate some kind of parameter from it. And then basically you are introducing a metric in the rule space, and then you can say, okay, these 2 rules are close because their associated parameter is also close. And then, of course, ideally you would want to introduce a parameter that will say something about the behavior. So, for example, there's a famous lengthen parameter that's often used for this, which is defined as just the number of ones in the rule table divided by the total number of entries in the rule table. So, for example, here, there are 8 total entries, 4 of which have as update value 1, so the lengthen parameter or lambda will be 1. So here it's shown how that can be used to impose a structure in the rule space that's useful. So these are the different Wolfram classes that Michiel already mentioned. Well, he used an extension, I think, of Lee-Packard classes. But so for a low lengthen, for low lambda value, you will have ordered behavior because there's not a lot of activity in the rule table. If it's a little higher, you will have still ordered behavior, but periodic. And for the highest values, you'll have chaotic behavior. And then class 4 lies somewhere in between, in on the road to chaos. Now, for a single lambda value, you usually have multiple rules that correspond to it. And if you traverse the rule space from order to chaos, 2 things can happen. So sometimes you can have an abrupt change from order to chaos, which corresponds to a first order phase transition, or you can have a more gradual change where order and chaos start to kind of mix, and then you have a second order phase transition. And it's exactly in this second order phase transition that class 4 is found. Now this is a bit curious that you have a mixture of both phase transitions when you go from order to chaos. And Lee and Packard proposed that that a one-dimensional structure is not enough. We need a 2-dimensional structure for the rule space. So they said, okay, on one axis we have the lengthen parameter, but then there is what they called a mystery parameter on the other axis. And he said if we could plot it like this, then we will see why we sometimes have a second order phase transition, which would be the green zone here, and sometimes a first order phase transition. Now, this will be kind of the point of my presentation. So I will discuss 3 sets of parameters that you can use to get this kind of phase diagram, and then see if we can see where the first order phase transitions occur and where the second order phase transitions occur. So in order to do this, I will also be using a nearest centroid classification to make it a bit more quantitative. So basically what this means is, so this is an example of how you could represent a rule space. So every point here corresponds to a rule in the rule space, and then you just take a rule and you compute both of its parameters, so you can find its location in the 2-dimensional plane, and then you color every rule according to its Wolfram class. So it's a supervised classification because you know the rule already. Yeah, so this is just an example of how the nearest centroid classification works, and later the axis will be labeled. And so for every class or for every cluster, you compute its average location, so its centroid. And then if you want to classify a new rule from which you do know the parameter values, but you don't know its class, then you just see which centroid it's closest to. That's basically what the background coloring represents. These are the decision boundaries. This way you can make the phase diagrams more quantitative. And you can also see, well, you will have a prediction score. So it will be, you can split your rule space into training data and test data. And then you can see how well it does at classifying a cellular automaton rule automatically based on the rule table. And that tells you something about how well these parameters are, how smartly chosen they are. All right, so the first set of parameters that I'll be considering are just the classical rule table parameters. So the lengthen parameter I already considered. And actually Lee and Packard, when they talked about this mystery parameter, the one that they proposed was the sensitivity, mu. And the sensitivity is basically the average of all possible Boolean derivatives that you can compute of the rule table. So basically it's it tells you about how strongly your cellular automaton will respond to a change in its input. Then, yeah, this is already, so this was an example of the phase diagram that they computed for this. So yeah, basically it's already what I said earlier about lengthen, where the different classes can be found. So basically I will be making a similar phase diagram, but yeah, in a more quantitative way. And I will also show that actually these two parameters, which they would often use to look for structure in the rule space, are actually not the best parameters to choose, and that there are better alternatives. Then I will also be looking at two phenomenological parameters, so being the average cell entropy and the average mutual information. So the average cell entropy, that is of a temporal sequence. So you take a certain cell and you look at its time evolution, its evolution over time, and then you get a temporal sequence. Then you can compute the entropy of that sequence. If you average that over all the cells in the lattice, then you get the average cell entropy. And then also the average mutual information. So the average mutual information between two cells is their entropy. So again, of the temporal sequence of the first cell plus the entropy of the second cell minus their joint entropy. So if these two sequences are completely unrelated, then the joint entropy will just be the sum of the separate entropies, and the mutual information is 0. It's only when they have some when there's some information that they share among each other that it will be non-zero. So basically it tells you how much information do you gain about the first cell if you know the second cell, or vice versa. And so the two cells that are used here are actually the same. So the cell and itself at the next time step. So we are looking at average mutual information over time. So basically the average mutual information will tell you how well the cellular automaton does at transmitting information from an earlier time to a later time. All right, and then the final set of parameters I will be considering are based on mean field theory, which I will introduce briefly now. So basically mean field theory asks you, in the binary case, if you know the density of ones at a single time step. So here we have a space-time diagram and the time axis points downwards. Then you have like a single configuration and you look at the density of ones. Then you ask yourself, okay, given this knowledge, what will be the density of ones at the next time step in a mean field approximation? Of course, you can do the explicit simulation, but just in a mean field approximation. So this involves two steps, basically. In the first step, given your density, you want to know what the probability is that every neighborhood will occur. So for example, you have here the neighborhood 1, 0, 0. Then you can just compute it by with this product of densities. So we have the density of ones to the power of 1, because there is 1, 1 in the neighborhood, and then the density of zeros to the power of 2, because there are 2 zeros in the neighborhood. And then, of course, you can write this as a function of just the density of ones, because they all sum to 1. And then to get the density at the next time step, you just sum over all those neighborhoods who have as update value 1. So basically, this would be these 4 here. You compute the probability that they occur, you sum them, and then this will give you basically an update equation. So basically what you do with mean field theory is you average over all the degrees of freedom, or over all the cells, and you reduce your cellular automaton to a discrete dynamical system on the unit interval. So you just have a real number in the unit interval with a certain update equation. But again, this is an approximation, of course, because it ignores all spatial correlations that exist between the different cells. And the approximation was made here, actually. So here we assume that the probability, for example, that the 0 occurs in the middle is just equal to the density of zeros, but that's not true because it depends. It's not independent of the value of its neighbors. So we should be using some conditional probabilities to be more accurate. So what you get then are mean field curves. So this is the result of our previous calculations. So on this axis, you have the density at the current time step, and here you have the density at the next time step. And as you can see, there are 4 different cases that can be distinguished, and they depend on the update values of the 0, 0, 0 neighborhoods and 1, 1, 1 neighborhoods. So if your 0, 0, 0 neighborhood has as update value 0, the intersection point will be here. If it has as update value 1, the intersection point will be here. Similarly, for the 1, 1, 1 neighborhood, it determines the intersection point at the other side. So in this case, where the update values are 0 and 1 respectively, you get a roughly linear relationship between the densities at the different time steps. And this will generally lead to constant behavior, which makes sense because if you start at a low value, at the next time step, it will also be low. And so you will kind of circle around the same point rather quickly and have a stable fixed point. In the converse case, where it's inversely linear, you will have more periodic behavior because, for example, if you start at low density, it will be high at the next time step. And then you end up here, and then it will be low again, high again. So you will kind of make a square around the mean field curve, which will cause periodic behavior. And then the final case, well, this is actually just one case because this case can always be transformed into this case. So you see these two cellular automaton are equivalent if you just relabel the values. So the dynamics is the same. So basically, we only need to consider this case here. And that's not the case here because if you switch around the values, you arrive at the same case back again, and here as well. But for these two are interchangeable. Now, here you see chaotic behavior, but that's not always the case for these kind of curves, and it really depends on the height of the maximum here. So to see why it is, we can look at the logistic map. So the logistic map is also a discrete dynamical system on the unit interval, and so it's very similar, the update equation, to mean field theory. And here you see the update value. So here you see the update equation for the logistic map, and here you see the function plotted for different R values. So again, it's very similar to this case here. And here you see the bifurcation diagram for different R values. And so for lower R values, you will have a fixed point. Then you have a period doubling bifurcation causing periodic behavior, and then you keep having period doubling until you get to chaos. And there are some stable regions in between, but generally you have chaotic behavior. And so we see a similar thing for cellular automata. So here you see the different, so this was globally called, all the curves with this kind of look are called nonlinear curves. And you see for a low maximum, you get a fixed point, a homogeneous fixed point, then it becomes inhomogeneous. Then you get period doubling, periodic behavior, and then for the highest values, chaotic behavior. And here, this is actually rule 110, so this is the class 4 behavior. So again, it's very similar to the logistic map, even though we are ignoring spatial correlations, so it's not always correct, of course. I guess a good example would be what Barbara talked about, the number conserving cellular automata. They are completely wrongly represented here because you only look at the density of ones, which will always be the same. So you will always have a perfectly linear curve, even though you get very non-trivial behaviors. So, but still, in general, you still get some good results. And so this is what led us to define the two parameters we will be using based on mean field theory, the slope and the nonlinearity. So the slope is just this point here. Now, of course, in the binary case, the slope will just have 3 possible values. Here it is 1, here it is -1, and here it is 0. But this only occurs for binary CA. So when we go to more states, the slope can have many intermediate values. And then also the nonlinearity, which is just the difference between like the connecting line here and the maximal of your curve. Okay, so this is the last set of parameters that I'll be using to look at the phase diagrams. Yes, then also I will not just look at some phase diagrams for one rule space, but I'll be considering 3 different rule spaces. So the first one is the elementary rule space. Then I'll also have look at a rule space with a larger neighborhood radius, so a neighborhood, a radius of 2 or a neighborhood size of 5. And then also a rule space with a radius of 1, but with 3 states. Now, in both cases, I will be only looking at the totalistic rule space in order to keep the number of rules low enough. Because, like I said, for now, it's a supervised classification problem, meaning that I had to, we had to go over all the rules in the rule space ourselves to see which Wolfram class it belongs to. All right, so here you see the nearest neighborhood classification for the phenomenological parameters. So basically, this is kind of like the benchmark and kind of the best possible classification we can have based on 2 parameters. Because they are based on phenomenological parameters, and the Wolfram classes are also based on space-time patterns. So these will always give better results than any rule table parameter because, there is the behavior of a stellar automaton is actually undecidable from the rule table. So yeah, basically what we see is that for class 1 and class 3, so for very ordered and for chaotic behavior, we have a low average mutual information in every case, which makes sense. Because the class 1 CA are just too simple to propagate information, and then the class 3 are too random to propagate information. Then class 2 is found near some higher average mutual information. And of course, we can distinguish class 1 from class 3 by their average cell entropy, because class 1 is very low, is near 0 in entropy, and class 3 is virtually random. And then here we see that class 4 occurs as a phase transition region. The size is different, but the location is the same between class 2 and class 3. Also, the prediction scores are quite good, yeah, especially here. But of course, this is the smallest rule space. Yes, actually, so this is the elementary rule space. This is the rule space for a larger radius. This for more states. Now, one thing, so this is the prediction score that you can see is that the prediction score of the elementary rule space is very low, and that's actually because there are a lot of rules in the elementary rule space that don't really do anything except for shift the initial configuration. So if your initial configuration is random, which is in our simulations, then also the configuration at a later time will be random as well. But that's not because the rule generates randomness, it's just because the randomness from the initial configuration is conserved. And we do not have that issue here because we're looking at totalistic rule spaces. And for a totalistic rule space, you cannot have a shift like that. But generally, when you go to larger rule spaces, this problem becomes smaller and smaller because the fraction of rules that do this will also become smaller and smaller. Then these are the phase diagrams based on the rule table parameters suggested by Lee and Packard. And as you can see, they actually do very poorly. So first of all, there is no global structure that's present in every rule space. It's different every time. Well, of course, there is some global, like when the sensitivity increases, you go from class 1 to class 2 to class 3. But also the prediction scores are very, very low because there are only 4 classes. So if you assign them randomly, you will still be right 25% of the time. And so here it's 24 actually. So it's actually incredibly bad. Now, 2 things that can explain this, of course, is that it will be better when you go to higher rule spaces because the lengthen parameter does a lot better for a very high K and a large number of states and a large radius. But also, I think the main problem was that they maybe didn't consider was that the sensitivity and length parameter just encode a lot of the same information. They are very correlated, so it doesn't really make sense to consider both of them at the same time, which is why the mean field parameters actually do a lot better. Now, of course, here we see 3 lines because, like I said, the slope can only have 3 values in the case of the binary CA. But here you see why we had to define it still, because yeah, in the case of stellar automata with more than 2 states, you still get a lot of intermediate values. And basically, it is what we would expect based on based at looking at the logistic map. We see that for a low nonlinearity, we have periodic behavior for a negative slope, constant behavior for a positive slope, and then we get our chaotic behavior for a very high nonlinearity. Now, the phase transition region lies in a different location in each position. So now we are also doing a lot of other tests with a lot of other rule spaces. And so generally we found that for when you do a high enough number of states and a large enough radius, you will find that the phase transition region lies actually on the triple point here. So basically, yeah, ignore this green at the bottom, and then you would see the phase transition diagram that we are now getting. So it lies somewhere at the triple point. But for smaller, especially for binary rules, it lies here, different in every rule space. Now this is also a bit logical because generally it's very, very hard to predict the location of class 4 based on rule table parameters, especially based on the mean field parameters that we proposed, because class 4 is characterized by being able to do computations sometimes and to process information. And in this case, it's very important to take into account the spatial correlations that can occur. And that's exactly what mean field theory ignores. So that's why it's sometimes a bit hard to find where class 4 lies. But still, so this basically summarizes the structure we were able to find right now. So yeah, so here again, low average mutual information for class 1 and 3, and then high for class 2 with class 4 on the phase transition region here somewhere. Yes, also we also did some tests already with more than 2 parameters. Of course, the more parameters you can have. But generally, we didn't find any combination of 3 parameters that were non-trivial or that give you really an extra dimension of information that was meaningful. So yeah, that was it. Any questions?
Thank you very much. Do we have any questions here from the audience?
So now, very nice. I was thinking that actually, in my opinion, no, the difference between class 1, class 2, etc., is related to the attractors. No? In general, class 1 has just a few attractors with a very large basin. Class 2 has many point-like attractors. And so on. So, have you tried to consider the Lyapunov exponents as? And I know that you work a lot with this because some sense it should be related to what we do with the classical dynamical systems.
Yes, indeed. So yeah, I mean, here I'm just showing some parameters, but we did consider a lot of different parameters, and indeed, Lyapunov exponents were useful. Even though I said that there's not really a lot of the third parameter we could find that didn't already correlate with the previous 2 ones. And the Lyapunov exponents, they were able to do that a little bit. And we are still working on that now. I'm working now on a bit of a new method to do the Lyapunov exponents, very similar to what you did, I think in the 90s a bit somewhere. But we are doing the same with the Jacobians, and then but doing also the diagonalization approach of and then we get very good exponents, and that's also something that we do plan to use.
You also work with the spreading, so the Lyapunov characteristics or something.
Yes. So if you do the diagonalization approach, you get basically the spread of your Lyapunov spectrum, which tells you a lot for the difference between class 3 and class 4. So yeah.
Thank you for this question, because I also wanted to ask about Lyapunov exponent. We have another small question, because you mentioned the case of multi-state automata and mean field approach, that it leads to the need for many values of those nonlinearity, right?
Yes.
Are there any other problems? And is mean field working better in case of binary automata, or is it the same if you have many states?
Well, it's working better for multi-state automata, but I don't think that's because there are more states, but just because there are more rules, and the larger the rule space, the more our results converge towards each other. For the binary case, the number of rules is so small that also the number of weird rules, like identity rules, is like the fraction of those rules is not negligible, which affects your results, which is why we had such a poor prediction score for the elementary rule space. But so yeah, I wouldn't say that they necessarily give better results, but they give good results. Well, they give better results, but not because of the multi-state.
Okay, thank you. Okay. Anyone else? If not, let's thank the speaker again. Thank you very much.
Thank you.
And now the third talk in this session will be online, right? By Henrik Fuchs from Rock University.
Can you try to speak?
Yes, can you hear me?
Okay.
Yes, we can.
Okay, good.
Okay, so the title is Algorithmic Beauty of Finite State Machines. Please present your talk.
Good afternoon, everyone. Thank you, Franco, for giving me opportunity to give this talk online. I really regret that I wasn't able to be there in person, but I'm in the midst of exam session now, so it was just not practical to come. If you look at the title of my talk, it should be clear that it is a paraphrase of a title of a book of Pruszynkiewicz and Lindermeyer, Algorithmic Beauty of Plants. If you have studied complex systems for a while, you might be familiar with the book. In this talk, I will not show as impressive images as Pruszynkiewicz and Lindermeyer did, but I would like to show you some interesting method, I hope interesting method of visualizing dynamics of cellular automata. So first, let me fix some notation. I will do a very few formal formulas. You will see a lot of formulas, but I will not use a lot of formal machinery. So what I need basically is two things. The notion of infinite binary sequence. So I will look at dynamics of elementary cellular automata in the space of infinite lattice, in the case of infinite lattice. So X will be a infinite binary sequence. Lowercase f is a local function of a cellular automaton. I will only talk about elementary rules with nearest neighbors. So left neighbor, center side, and the right neighbor. Capital F corresponding to lowercase f will be a global function. So this expression on the left-hand side is the state of site I after one application of the rule. I will also need the notion of block mapping. The block mapping will be bold f corresponding to regular f, which is a local function. And what block mapping does, it's easiest to explain on an example. It is a function which is applied to finite blocks or words, final sequences of symbols, in this case from A1 to A8. And what you do is simply compute the next value of those symbols by applying the rule. As you can see here, we cannot compute the next value of A1 because we don't know what is the left neighbor. It's a finite string. But we can compute for A2. So A2 becomes B1, and B1 is just F applied to this triple A1, A2, A3. And of course, we do it simultaneously. We apply it to all sides, and we obtain a string or block which is shorter by two sides. So F of A is a shorter block, in the case of elementary rule, shorter by two sides. And of course, we can repeat this operation as many times as we want until we hit a single side or a block of length 1. One more thing which I will need is the notion of what I call density polynomial. It's a very simple function denoted by psi with index A. And if A is equal to 1, this function does nothing. It just behaves like identity. So psi of P equals P if A is 1. If A, on the other hand, is equal to 0, it performs Boolean conjugacy or flipping the bit. If P is a Boolean variable, 0 or 1, taking value 0 and 1, it simply replaces 0 by 1 and 1 by 0. So I call it flipping the bit operation. Now we can define similar function associated with finite string B, with block B. And what we do is simply apply that function to every argument of the function. Of course, the number of arguments here has to be the same as the length of the block. So we apply it to every single argument, and as index, we take consecutive bits of this block B. Now, again, it's easiest to understand if you look at a concrete example. So let's say that our block is 0, 1, 0, and we want to compute density polynomial for it. What we do is simply replace 0 by 1 minus p. So this first 0 is 1 minus p1, the second 0 is 1 minus p3. And the only non-zero side here is 1 in the center, so that one in the center is just unchanged. So it's easy to see that this function, this density polynomial, is simply indicator function of the block B, because if p1, p2, p3 is 0, 1, 0, then this function will return 1. For all other values of p1, p2, p3, it will return 0. Now, why is that useful? Well, it's useful because if we have something like this, we can construct explicit expression for value of side j after n iterations of the rule. So that's what this expression does here. We apply function, global function n times, and we want to know what's the value of side j. Now, of course, this will be simply sum of indicator functions of all pre-image of ones in n step by applying it will be a set of blocks, indicators function of a set of blocks which produce 1 in n step if we apply block evolution or block mapping function n times. Of course, this looks like almost having a closed form solution in quotes of cellular automaton, but the problem is that this expression can very quickly become complicated. Let me show you what it does on concrete example. So for example, in case of rule 184, elementary rule 184, which is known as traffic rule, the only triples or 3 blocks which produce 1 are those shown here. So I say that the pre-image of 1 in 1 step under this rule are those blocks. So for each of them, what I need to do is to produce a corresponding density polynomial, and I do it in the usual way. So 0 is replaced by 1 minus argument, and I denote 1 minus argument by x bar. So x bar is simply 1 minus x. So as you can see here, I have 0, 1, 1, and that corresponds to the first block. Here I have 1, 0, 0, so both those are flipped, and 1, 0, 1, and so on. Of course, I could do this for higher order iterations. For example, if I do it for 2 iterations, then what I need is all blocks which produce 1 in 2 iterations. And there is actually 16 of such blocks. And for each of them, I would have to construct corresponding density polynomial. And I only show here first two of them. So for example, 0, 0, 1, 1, 1 becomes xj minus 2 flipped, xj minus 1 flipped, and then the remaining 3 are unflipped. So xj, xj plus 1, xj plus 2, right? And the same thing for this one. So if I wanted to produce complete density polynomial for the second iteration of my rule 184, I would have 16 terms. So this becomes complicated pretty quickly. So the interesting question now is, can we construct some sort of closed form expression for such density polynomial for n iterations? So not for just 1 or 2, but for arbitrary n. Is that possible? And I will show you in the next slides that indeed, in many cases, it is possible. And in effect, it means that we can actually construct solution of the initial value problem for cellular automaton, because we can find expression for value of side j after n iterations if we know the initial configuration. Now, before I do this, I will very quickly describe the the concept of finite state machines, because that's what I'm going to use here. Finite state machine, if you have background in computer science, you're familiar with this idea. It's basically a machine which can be in exactly one state of a finite number of steps at any given time. And it is usually represented by a graph. And here is an example of such graph. This is a finite state machine which can be in 5 different states. So those circled numbers denote states of the machine. So the state of this machine can be 0, 1, 2, 3, 4, or 5. Initial state of the machine is bold circle, and the final state is double circle. Now, what the machine does, it can move or make a transition from one state to the other, and the transitions are represented by edges, directed edges, and each transition is associated with a symbol. So the symbol is marked as a label on the arrow. Now, each path from the initial state to the final state corresponds to a string of symbols. In this case, for example, if I go from here to here, it will correspond to 0, 1, 1. Now, if there exists a path corresponding to a given string of symbols, we say that such string is accepted by the machine. If it doesn't exist, we say it's not accepted. So that's basically all what is to it for finite state machines. Now, let's apply this idea. Let's try to construct finite state machine corresponding to pre-images of blocks. So I will start with something simple, what we already did before. Rule 184, one-step pre-images of 1. So those are 4 strings. And what I did, I constructed here what I would call a row finite state machine. It's a machine which has many, 4 in fact, end state, final states, 1 initial state, 0 here. And as you can see, there are 4 paths from the initial state to the final state, each of them with labels of edges corresponding to those strings. So 0, 1, 1, that's the first, and so on. Now, I call this machine row because it has some properties which are not really desirable. Main thing is that it is a machine which is called non-deterministic, because if the first symbol is 1 in my string, I have 3 choices of the next state of the machine. There is a way to transform my machine, such a row machine, into a deterministic machine where no 2 edges leaving the same state carry the same symbol. And here is the result of application of this algorithm of determinization of a finite state machine to my case. I will not go into details how it's done, but sufficient to say that there exists an algorithm which allows you to do this for every finite state machine. So when we do this, in our case, we get a machine which, as you can see, is deterministic. For example, from state 0, you can go to 2 different states, but each edge carries a different symbol. Now, this machine still has some problem, namely, it has many end states, many final states. And there is a method for transforming this machine even into a simpler one, and it's called minimization. Again, there is an algorithm for minimization. I will not go into details of it. I am using a ready-made software for this purpose. I am using a library called AT&T Finite State Machine Library, which has minimization algorithm built in. And when I applied this to my finite state machine from this example, what I obtained is something like this. So as you can see, it is a machine which has a lower number of states than the initial one, and even than the deterministic one. This one had 9 states, and this has only 5 states, and only 1 final state. And of course, the same 4 strings as before can be represented by paths on this machine. So what I will show you now, I will show you finite state machines for various cellular automata, machines which are deterministic and minimized by using exactly this software, AT&T finite state machine library. So let's start from consecutive rules, elementary cellular automata rules, rule 1, rule 2, 3, and so on. So if you do it and construct finite state machine for, let's say, 5-step preimages of 1. So in other words, strings which in 5 steps, 5 time steps, 5 iterations produce 1. And you will see that for rule 1, we have a very nice linear machine. Of course, that's after minimization. You will see a lot of double edges, which basically means that those symbols, first, second, third, and fourth symbol here, doesn't matter. It can be either 0 or 1. Then the next 3 symbols are fixed, and then again arbitrary sequence of symbols. For rule 2, we get slightly different machine, but also nice linear. For rule 3, again, very nice linear machine. For rule 4, same story. For rule 5, nice linear machine. So you could already get a naive impression that it's like that for all rules. But let's do it for rule 6 and see what happens. And here's what we get. And that's unfortunately not as nice as it was. And it shows you some sort of a bimodal distribution of those machines. Either they are very nice symmetric machines, or they are very messy, very complicated with very high number of states. And for rule 6, we can see that that's the case. There's really, it's something which is almost not readable, not human readable, in the sense that we cannot see any structure in it. Let's go back for a second to rule 1, and I will show you what happens with when we actually compute finite state machines for different number of steps, for 1, 2, 3, 4, and 5. As you can see, such nice linear machines are obtainable only for odd ends. For even ends, we get something slightly different. So let me first concentrate on odd ends. For odd ends, that's what we get. N equal 1, 3, and 5. And you can see that basically the central part here stays the same. And what only happens if you increase n is that you add a larger and larger number of arbitrary symbols. So this is here actually the central site J. Those are its nearest neighbors. And it's easy to see from here that density polynomial associated with preimages of 1 are basically density polynomials of 0, 0, 0. So xj minus 1 bar, xj bar, xj plus 1 bar. And this expression tells me what's the state of site j after n iterations of rule 1. So I, in a sense, obtain solution of initial value problem for this rule. For odd ends, it's slightly more complicated. It is at least the central part of the machine is a little bit more complicated, but it's the same in n equal 2 case and n equal 4 case, and in all other even cases. The central part stays the same, and there are just some arbitrary symbols added afterwards. So what you could do here, you could construct density polynomial for all paths of this central part and simplify it. And it turns out that actually if you do this, it factorizes to something really nice, to expression which I show you here at the bottom of this page. So if you summarize this, we can say that we obtain solution of the initial value problem for rule 1, explicit expression for state of cell j after n iterations, and it's shown here. Of course, there are 2 different cases for even and odd ends. For other rules, you can do the same thing. I will not show the process, but you can obtain similar expressions, sometimes a little bit more complicated, like in case of rule 3, sometimes less complicated, like in case of rule 4. But basically, those are all solvable rules for which you can write explicit solution of f and j in terms of initial configuration. So what we could say is that we have sort of two methods of describing what happens. We either use formula for solution of the initial value problem, but the same formula can be represented by finite state machines representing pre-images of 1. Are those two methods equally good? And I put good in quotes because it's at the moment not clear what I mean by that. Let's take a look at some further examples. Here's an example which I like very much, one of my favorite ones. It's rule 162. Finite state machine for this rule has a very nice symmetric form. A lot of regularities. You can see we go down and up and down and up and down and up. And here there are two edges, 1, 2, 1, 2, 1. So a lot of symmetries. You can construct formula for it from that machine. I have no time to explain what are the methods. There are various methods for constructing such formula which you can apply. Anyway, the formula here is also very elegant, compact, closed form of the solution. So state of the cell J after n iterations is given by this nice expression. So this is a case where if we use our beauty paraphrase, that both finite state machine and formula are very elegant. I would even say beautiful. For rule 105, another example of nice finite state machine, we have the same situation. We have very nice symmetric finite state machine, and we have a reasonably compact formula. Again, I will not go into details how it was obtained. This is a slightly different type of formula. It uses so-called trinomial coefficients, which are generalizations of binomial coefficient. So they are coefficients of expansion of trinomial raised to the nth power, and you can express state of cell J after n iterations by those trinomial coefficients. Again, nice formula, nice finite state machine. For rule 14, we have maybe less obviously symmetric finite state machine. Formula can be obtained. This is kind of a borderline case in terms of aesthetics. We of course have cases where it is the opposite, where the machine is very messy, like this one. So it's very difficult to figure out what's going on here from the machine only. But nevertheless, it is possible to obtain density polynomial, again by method which I called pattern decomposition. I have no time to show how it's done. Perhaps in the publication, if we have proceedings publication, I will explain details of this. There are nicer cases, however, and I would like to spend the remaining few minutes to talk about those. For example, if you construct final state machine for rule 184, the traffic rule, you get a very interesting, almost a square grid pattern, and it is actually better to put it on the grid, like here, equal spacings between nodes. And that's the machine. That's the final state machine for rule 184. As you can see, there is a lot of regularity here. And what I put here below is the description of edge labels for horizontal. Edge means horizontal. So those labels are either 1 or 0, and there are reasonably simple expressions for those. For rule 142, which is another rule of this type, we can have similar finite state machine, Very nice, very symmetric, surprisingly symmetric finite state machine. As you can see, I labeled states of the machine here slightly differently. They are simply labeled by coordinates of those nodes. So it's 0, 0, 1, 0, 0, 1. This is just to describe the machine a little bit easier. And again, expressions for edge labels for horizontal and vertical are fairly simple. Rule 14, also very interesting machine. It has this indentation here, so it's like those nodes are lacking, but otherwise it is remarkably similar to 184 or 142 machine. Now, are those things useful? Well, again, without going into details, yes, if we have such regular finite state machines, you can do a lot with them. In this case, or in the case of rule 142 or 184, we cannot obtain explicit formula for density polynomials. At least I don't know how. I spent a lot of time trying. But it is an example where we have a very seemingly simple and beautiful finite state machine, but no formula. Formula, if it exists, it will be extremely complicated, which is a bit surprising. But it is a case where finite state machine describes those cellular automata in a sense, in an easier fashion than formulas would, because formulas would be, if they exist, would be very complicated. You can use such machines to do many other things. I will just mention one thing. You can, for example, compute probabilities of occurrence of a given symbol or a given block after n iterations of the rule if you start from random initial configuration. Just an example of such result, for rule 142, you can compute probabilities of various blocks. Those blocks which you see here are so-called fundamental blocks. Knowing those four, you can compute probabilities of any other block of symbols of length up to 3. So for rule 14, 184, and also 42, 43, I'm sorry, we can obtain similar results. Now, sometimes you can have very complicated finite state machine, but nice formula. And here is an example. For rule 50, there is a very elegant formula for solution of the initial value problem. And that's something you would not figure out from the finite state machine. So sometimes finite state machines are better to describe the rule. Sometimes formulas are better, because in this case, this is a formula which is human readable, whereas the machine, well, it's difficult to see in the structuring. Of course, there are opposite situations. Here's an example of rule 38, where the formula is rather ugly. I obtained this formula again from the machine, actually. But the formula is complicated, has 3 different cases. But the finite state machine is more compact, and I think it's more elegant than the formula itself. So sometimes machines are better, sometimes formulas are better to describe the rule. Rule 156 is another example where the formula is very, very complicated. This is something I have obtained very recently, again by a method of pattern decomposition, which I will not describe here. Very long formula with several terms. But the final state machine, well, it's hard to say whether it's beautiful or ugly. It has some structure, but again, not easy to see from just visual inspection of the machine. Of course, it gets worse. If you look at rules of class 4, like rule 110, which is known to be computationally universal in the sense that it can emulate a universal Turing machine, the finite state machine is a mess, and of course, formula doesn't exist. There is no hope that formula would exist, because, as I said, it's the universal computational universal rule. what I started doing recently is experimenting with three-dimensional layouts for those machines, hoping that perhaps by looking at the machine in 3 dimensions, some structure which is hidden in 2D might appear obvious in 3 dimensions. I don't really I couldn't find any good software for visualization and layout, an optimal layout of 3-dimensional graphs. Perhaps if somebody knows, I would be happy to hear suggestions. What tools could be used for 3D visualization of graphs, of complex graphs. Anyway, so I showed you some examples of both formulas and finite state machines, some very nice, some rather ugly. Of course, as they say in English, beauty is in the eye of the beholder, or as Shakespeare wanted to have it, beauty is bought by judgment of the eye. I do not quite agree with that. I think there is objective notion of beauty, and to me, it's definitely this machine. This machine is nice and beautiful, beautifully symmetric. This one is messy, and you know that the same applies to architecture and other things. So thank you very much. That's basically all I wanted to say. For some reason, I can't hear anything. Is there? So unfortunately, my sound, for some reason, something happened. I can't hear anything. And I checked my settings. I don't know what's going on. My apologies. I can see the chat. So if there is a question, if it's not long, if one could write the question, if there are any questions in the chat, that seems to be the only possibility because I can't hear. Thank you. Okay, so the question is how to change from non-deterministic to deterministic machines. Yeah, so you know, those machines, the deterministic, it really is not. I think the name is a little bit misleading because what it really means is that you have There is no randomness in it, because non-deterministic would imply that there's some randomness. So all what this does, this algorithm, and I don't, and unfortunately do not know details of how it's done. What is the algorithm? There exists algorithm for doing it. All what it does is it reduces the number of states in such a way that no two edges leaving the same state carry the same symbol. But this doesn't mean that this is in any way probabilistic. It just means that you have a choice of going to 3 different states, where here it is done in such a way that you don't have the choice. That's all what it is.